Hello, everybody, to this third clip of the course of modern wireless communication and applications. This is in part two. So part two is related to digital communication, and now we are in clip three. In the last part of clip two, we reached to this slide about binary digital modulation, and we can see here the three famous kinds of modulation that amplitude shift keying with the information signal or the data is like augmented in the amplitude of the carrier. In the FSK, it is in the frequency part, and for the phase shift keying, it is in the first part. Actually, the phase shift keying is binary phase shift keying is one of the most important modulation techniques in digital communication due to its high performance. And performance here, I mean in the probability of error. So this is the best one in terms of probability of error, that it has the highest like reliability when you transmit the digital signal. And X of t can be, for example, like antibodal, like +1 and -1. So once x of t is +1, then 1 minus 1 is 0. So we don't have any phase shift. And once it is -1, it becomes -1, -2, -1 is -2, and -2 divided by 2 is -1 times pi. So it is minus pi. So it means that when you have the first symbol that you send simply like a cosine 2 pi f0t, and when you have the other symbol you send, for example, this is symbol s0, and for s1 you send a cosine 2 pi f0t minus or plus pi. So the difference is 180 degree. Okay, and why this one it has the best like performance? This is what we are going to see in this slide. So you can see here that the difference between those two symbols is 180 degree. Okay, so the distance is the largest, so the distance here is equal to 2a actually. So in order, if you send s0, when it is possible for the receiver to misdetect it, or it will like make error in the reception. So it means that you send s0, but the receiver will say that it was s1. This will happen if s0, due to noise and due to for example channel the corruption, that it will be received somewhere here. If it was received somewhere here, so of course the receiver will say that the transmitted signal was S0, because now it is closer to S1 location. Okay, but this to happen, this S0 should be shifted by more than a in order to get this error. This is much better than, for example, orthogonal systems, because in orthogonal system that we might have this case. So we have, for example, this is for S0 and this is for S1. We have 90 degree between them. So now if this is A and this is also A, okay, and then the distance now between these two symbols is square root, because this is a and this is a, so it will be square root of 2a. This is the distance between these two symbols, which means that if due to noise this is 0 moved somewhere closer to the place where the decision boundary of S1, then the receiver might detect it incorrectly that as S1. But now the distance is just is square root 2 of A. However, here the distance is 2A, which is 2A, of course, is larger than square root of 2A. This indicates that the binary phase shift keying actually is better than the orthogonal modulation. Okay, we will see more about the other performance measures like the spectrum efficiency about this one, how to increase the spectrum efficiency in case of phase shift keying. But before that, let us see how to make the modulation of binary phase shift keying. So simply that we have, if we have like 0 and 1, the data, we convert from 0 and 1 digital signal, BCM for example, into non-return to 0, or it is called antibodal, like you can see that plus V and minus V. Okay, and then we make multiplication in the carrier frequency cosine 2 by f0t, so it becomes plus a cosine for the transmitted symbol, for example, is 0 or is 1, and for the other symbol it becomes minus cosine. Minus cosine means that we have phase shift with 180 degree. Then we have bandpass filter, uh, related that for only around the carrier frequency, and then we transmit the signal. In the receiver we have also bandpass filter around the frequency that we want to receive, and we can have also some coherent carrier recovery from the received signal, because as we mentioned before, if your carrier frequency is exactly f0, the received frequency will not be f0, because due to Doppler effect, because of due to the channel, the received frequency can be f0 plus some delta frequency according to the speed of the transmitter or the receiver, or the dynamic dynamicity between of the channel, for example. So anything moving the channel might change the received frequency to another like some shifted frequency. Of course, this shifted frequency is very small usually, but still it will affect the accuracy of the detection. So to overcome this problem, we need what is known as coherent carrier recovery to minimize the effect of the frequency shift. And after that, as we see before, that the second multiplication of the cosine, we will have the signal to be shifted to the right and to the left. And to the left means that it is the original signal in the frequency domain, as we mentioned in part 1. And now we have low pass filter plus amplifier, then we get the original signal again. So this is simply the modulation and demodulation of the binary phase shift keying. So now let me have the blank screen to discuss one thing. So we have, as we mentioned, that we send either F like S0 or S1. Okay, I will take the screen in the front of me so it becomes easier to write. Maybe you don't see me, but it doesn't matter. So now we have like the transmitted, once we have only two symbols like S0 and S1, then what we do is that we send, this is like, as we mentioned before, S0 and S1. But in that case, every transmission carries only one bit. Okay, now if we want to send, let's say, 2 bits per transmission, what that means that a cosine 2 by f0 t, then it becomes plus phi. Now this phi I, the face of the data, is not carrying only two faces, either zero as in this case, or pi, but we want to have four different faces. So we want to have phi 0, phi 1, phi 2, and phi 3. So in that case, we have three different faces could be transmitted. Since we have four different faces, in that case, we can, in each transmission, this could represent 2 bits instead of 1 bit. So it can be, for example, 00, 01, for example, 11, and 10, as you can see. So in that case, this could be done like in circle here. See this circle. So now we have this face phi 1, maybe this is phi 2 and phi 3 and phi 4. Now I sent four faces instead of two faces. Um, what is the benefit of that? The benefit that we can increase the transmission bitrate without increasing the bandwidth, because the rate of the change of the phase is still the same. For example, if the phase is changing like 1 mega times per second, okay, 1 million times per second, the face is changing after like 1 million times per second. Now if we have only two faces, then we can send 1 megabit per second. But now for every change in phase, we send 2 bits. It means that now we have 2 megabit per second. Okay, now what if we have 8 faces like this one? So we have more faces. Okay, now we can send for over each face 3 bits, and then the bit rates becomes like 3 megabits per second, and so on. Actually, we can increase them like 4 megabits per second, 5 megabits per second, and by increasing the number of phases transmitted. And you can see that we still use the same average power, because the power is related to this magnitude a. So the power is related to a, sorry, a squared divided by 2. Okay, so the power is fixed. The power has we didn't change the power, and we didn't change the bandwidth, but we increase the bit rate within the same spectrum. The question now, what we will lose? We know that in this life nothing for free. So increasing the bit rate, the data rate, without increasing the power, but what we will lose. This we will see. Let us go back to our slide. So we can go to our slide. You can see. So this is what I just described over the blank slide, that increasing the symbols. Okay. Um, what we lose here actually is increasing the probability of error. This is the cost that we will pay by increasing the number of bits per phase. So in case of only 2 symbols, as let us go back. Yeah. So for example, in this case, as we mentioned, that if we send S0, the error will happen if the received signal was somewhere here. Okay, but what happened? Sorry, for the case of like 4 faces, now you send S0. Okay, because you sent S0, you will not receive S0 in this location due to noise and due to the channel problems. You might receive it here or here or here or here. You can receive it anywhere actually. So if you receive it very close to S0, our receiver, how it works, it will measure the distance of the received symbol compared with all possible locations. For example, if you receive it here, okay, then it will measure the distance between S0 and the distance with S1 and the distance with S3 and so on. So it is clear that this symbol is closer to S0, so it will be correctly detected as S0. But if the noise was a little bit large or larger, so that you sent S0, you received something here, okay, or you might receive it here. In this case, your receiver, when measure the distance, they find that this one is closer to S1 than S0. So it will detect it in error that it is the transmitted symbol was S1, but actually it was S0, not S1. Okay. Now, when we increase the faces even more, then the distance between the possible faces becomes even closer. So now this is 0. Even small noise, it can cause error. Now, if it is smaller, even smaller, then it becomes even more sensitive to noise. So this is actually what we lose. By increasing the number of bits per symbol, it means that our system becomes more sensitive to noise and interference and noise and channel problems, and the probability of error will be increased by increasing the number of bits per symbol. Okay, so this is what we need to make like trade-off, because also of course when we increase the number of bits, we can also increase the number of bits for coding, and we mentioned before that the coding can also detect and correct errors, and also we can manage by increasing power. For example, if it is allowed to increase the power from this, for example, A1, to increase it to, for example, to A2, so you can see that we will send those faces over larger circle, which means that we can increase the distance between the symbols at the receiver part and reduce the probability of error. Okay, and also there are some other techniques as we are going to see to show soon. But anyhow, before that, let us see here that, for example, if we have symbol S0, which represents the bits 000, then the phase is 0. If we have 001, then we have 45 degree, 011, we have 90 degree, and so on. So this is the distribution of the phases. Yeah, maybe you can see that the series of those bits following what's known as gray code, and you can see that the change between each one and each symbol and the next symbol is only 1 bit. Okay, so this is 000 001, so the change is 1 bit. Here is 011, so the change is 1 bit. The reason of that, if we go back to this one, for example, this is in the case of 8. So if S0 and S1, there is the most probable that error will happen. If you send S0, most probably that the error will be detected as S1 or S7. It is less probable that it will be detected as S2 because it is more far away from S0. Okay, in that case we try to keep the code. For example, if this 000, we want to keep this as 001, and we want to keep a 7, for example as 100. Why? Because we want, if error happen, that the error will happen only in 1 bit, not 2 bits. When there is only 1 bit error, then there is higher chance to be detected and corrected by our channel codes, our channel coding. Okay, so this is the reason that we use gray coding in the in this distribution of bits per phase. Okay, and now let us go to see. This is the, of course, the way that we have different phases, as you can see here, and we can expand this A0 cosine, because now we have different phases, not only 2 phases, we have many phases. It is M-ary. Okay, so we have M phases, M different phases, and in that case, we can expand it. Cosine can be expanded in this way, that cosine times cosine of this phase minus sine of the carrier times sine of this phase. But you can see here, still the amplitude is fixed because we didn't change the amplitude, we changed only the phase. And this is the way that how to modulate or how to implement this M-ary phase shift keying. So we have the bits here, we make the phase mapping, as we saw in the previous slide, that when we have this table, so we know that every 3 bits, for example, will be implemented at certain phase. Okay, and then we multiply this phase, or we use cosine for this phase and sine of this phase, as it is shown here. This is the cosine of this phase and sine of this mapped phase, and then multiply the cosine one with cosine, as you can see, and the sine one with sine, as it is here. And then we use band pass filter. Then we have the in phase part or component, and the quadrature phase component of the signal, and we add them together, and then we have M-ary phase shift keying output. Of course, then we can use like up converter of the frequency, and after that maybe power amplifier, and then the antenna. This is the how to generate the M-ary phase shift keying. How to demodulate it is also very easy. So we have the band pass filter in order to take the band where our signal is there, and then again we use carrier recovery to get the cosine 2 by f0t, and then we multiply the signal by the in phase by cosine and the quadrature phase by sine, then we get I and the Q. Then we use low pass filter, then we will get the magnitude is fixed. So by using mapping, lookup table, if we found the signal phase, for example 45 degree, of course we need both of them to know, sorry, the phase, the phase signal. So once we know that it is 45 degree, we have the lookup table that we showed before, then we can decide the number of bits generated at each time. Okay. Okay, we will talk later about the performance or the quality of service in digital communication, but now we need to concentrate about the most important one, which is the probability of error. So the probability of error is the one which determines the quality of digital communication, because if the probability of error is very, very high, in order that our channel encoding or the channel coders were not able to detect and correct those errors, then the communication might fail. So it is very important to specify the quality of the digital communication based on the probability of error. So again, the probability of error happened when the receiver decide that the transmitted symbol was SK, however that the transmitted symbol was something else. So it was SJ where J does not equal to K. Okay. We saw already this array phase shift king. So here we have the quadrature amplitude modulation. The quadrature amplitude modulation actually is very similar to M-ary phase shift king, but there is very important difference here that the amplitude is not fixed. So we can use different amplitude. So you can see that this one it has small amplitude, this one it has larger amplitude, this one has the highest amplitude. So the amplitude is different based on the symbol. Actually, this gives us first one more degree of freedom, because we can actually uh, transmit those which has higher important or importance of our digits. We can put them with higher amplitude, which means that we increase the uh, the probability that they will be detected correctly. Okay, so especially that when we keep them away from other symbols, and also we can optimize now. Now we can optimize between what? Between the power, transmitted power, okay, average transmitted power, and we can optimize also with probability of error. So we can optimize between the probability of error and the transmitted power in order to get the best performance. Before, in M-ary phase shift king, we have very limited because the power is fixed. So we don't have this degree of a freedom to select the power. But now we can change with the power. We can play with the power. Of course, we can the average power. We can based on the average power or the maximum power. We can also get much better digital communication or digital link performance now, because we have two things to play with, or degrees of freedom. Here we can see here it is 32 QAM, where we can send like 4 bits, sorry, it is 16 QAM, where we can send 4 bits per symbol, as you can see. So we send uh, if each symbol carries 4 bits. Okay. And again, if we want to compute or to see the transmitted symbol for each data, that it can be expanded as before as cosine, like in phase and the quadrature phase. The only difference between M-ary modulation and the quadrature amplitude modulation is that in M-ary the magnitude is fixed, but here the magnitude is also variable. So the magnitude here is depends on the symbol itself. So for the kth symbol, each symbol here it is on phase and it is on amplitude. And when we say it is on amplitude, it means that also it is on power. Okay. And as we mentioned before, that when we talk about spectrum less than 5 gigahertz, most of the spectrum is already occupied and licensed. And because of that, of course, except very small bands left free, as we mentioned in part one. But this makes the in digital communication, the optimization or the efficiency of using the spectrum is one of the critical topics in digital communication or in communication in general. And this spectrum efficiency is usually measured by bits per second per hertz. So in each hertz, how many bits per second you can send. Okay, for example, in binary phase shift keying, you can send only 1 bits per second per hertz. So this is the efficiency, the spectrum efficiency of binary phase shift keying. However, binary phase shift keying, it has the best in terms of probability of error, but it has also very low efficiency in terms of spectrum efficiency. And by the way, this is not the throughput. This is the data, transmitted data, which means that it is including also the coding bits and other bits, not only the information. So it is only 1 bit per second per hertz. Okay, but if we talk about 16 QAM, as we show in the previous slide, 16 QAM, it means that we send 4 bits per symbol. And 4 bits per symbol means simply that it is 4 bits per second per hertz. 4 bits per second per hertz, which means that a spectrum is much better than only 1 bits per second per hertz. However, then we are like we might face higher probability of error, and we should use better like channel coding techniques to detect and correct those errors. This is the Spectrum license in US. So you can see maybe the picture is not that clear, but you can anyhow find it on the internet. You can find the United States frequency allocations, the radio spectrum. So you can see that the license is here. So everyone is it show you what is the license of using that spectrum. So it is not a free. Because of that, it is very important to have the highest spectrum efficiency or the best possible spectrum efficiency. Of course, now in the 5G and for the future, we start to think about frequencies more than 5 gigahertz, like in the millimeter waves, where there are a lot of white spaces there or unlicensed frequencies there. However, there is a problem, as we mentioned in part one, that when you use very high frequency, like for example 20 giga or 30 giga or 40 giga, yes, you have plenty of spectrum that you can use. However, the coverage or the propagation behavior of that frequencies are not that good. So it can be used for short range or for like in corridor or something, but you cannot cover a city or for example by 50 giga or 60 gigahertz, because unless you will need very high power, and also it will be like it will have also some, it might have some biological impacts of using high power at that very high frequencies. Okay, digital receiver, actually we mentioned already some digital receivers before, but now we would like to give only the concept of the digital receiver in digital communication, like correlator receiver. The correlator receiver is simply working like that. You transmit your signal. So this is the received signal. After demodulation, of course, after demodulation, after filtering, after everything, what you will get your transmitted symbol Si, okay, plus noise. You cannot get rid of noise. Noise is there, and actually, if we want to be more accurate, we should also multiply this Si by some factor like alpha t, which represents also the channel. But let us make things easier, so we don't talk about the impact of the like inter-symbol interference. Let us assume that we have receiver that was able to remove the inter-symbol interference due to the channel and channel fading problems. Okay, now you have the transmitted symbol Si, and you have the added noise NT, that this is the noise which is generated inside even the circuits of the receiver. Okay, how could we detect this signal? This is called correlator receiver. The correlator receiver is simply based on the making or measuring the similarity between the received symbol or the received signal with all possible symbols. If you remember when we talked in the beginning of clip 1, that the benefit of digital communication, that instead of sending analog signal, now we send symbols, and those symbols are known also to the receiver. The symbols are known also to the receiver, but the receiver doesn't know which symbol was transmitted now. Okay, so the receiver knows that this symbol Si that we don't know is one of those, S1 or S2 up to SM. So we have here up to SM. This is for M-ary transmitter. Now we have R of t. Actually, we don't have Si. If we have Si, just Si coming, so the reception will be 100% correct. But we have this one, but corrupted by noise. We have noise. So what we have R of t. So here we have R of t. So what we will do, we will build what is named as maximum likelihood receiver or correlator receiver, that we measure the similarity between this R of t with S1, this R of t with S2, the same R of t up to Sm. We measure the similarity. How to measure the similarity? Mathematically, it is called correlator. The correlator, it means that you multiply this received signal R of t by S1 of t, okay, and you take the integration over one simple time from minus ts over 2 to ts over 2, or from 0 to ts. So it is over one simple time. You take this averaging. Actually, this is multiplication and averaging. Okay, and then you see for this signal, you have Z1, Z2 up to Zm. The maximum Z out of those will most likely, not necessarily, but most likely will be the transmitted one. For example, if Z2 was the maximum, so Z2 is it was the maximum of Z1, Z2 until Zm. So if Z2 was the maximum, this means that most likely that this Si is S2. The transmitted symbol was the symbol 2. Okay, so this called maximum likelihood receiver or correlator receiver. Okay, and this is the actually the optimum receiver, that it measures the minimum distance between the received signal and all other possible receivers. So in Euclidean space, that it can be measured as the distance. For example, if we have four symbols like S1, S2, S3, S4, and you receive something like here. Okay, so what you are doing, this correlator receiver, you measure the Euclidean distance. If we convert this into vectors with S1 and with S2, with S3 and with S4, and of course you will take the minimum distance. You will take the minimum distance to say that this is the most likely the transmitted symbol. Okay, so this is the same what we are doing here, but here we are doing it in time domain, and here is just when if we deal it as vectors, but actually in practice we do it in time domain as it is shown here with the correlator receiver, which is part of what is known as matched filters. But we are not going to talk in more details about this, but I want you to remember that when you see correlator receiver or maximum likelihood receiver, simply it means that we are looking for the symbol which has the closest or the highest similarity with the received signal. This is the main issue here. So you can see, for example, if we have S1, if we send this is S1 and S2, this is S3 and S4. Okay, so the received signal actually it will not be exactly the one that you sent, but it can be something like that. It can be, of course, it can be shifted somewhere. So this is S1. If S1 was received here in this area, of course our receiver didn't know that this is S1 in because of noise. Actually, it was received here as it is shown, so they will decide that it was S2, and of course this is error. Then we will have error in the detection and so on. So you send S4, you might receive it here, you might receive it here, you might receive it here, and of course, most likely, of course, you will receive them in the same area if the noise is okay. But the noise, you know that there is no limit for the noise. So the noise or for example, the channel, due to the channel properties, due to fading, the signal can be moving anywhere. So as far as we can keep this probability of error small, then we have successful digital communication system. So this measured by, as we mentioned, that measured by the probability of error. So probability of error is one of the most important performance measures in digital communication systems. Okay, and the probability of error is related to the signal to noise ratio. The signal to noise ratio. So mathematically, we measure we can estimate the probability of error based on the signal power divided by the noise power. So if the signal power divided by the noise power is high, then we have high signal to noise ratio, which means that the probability of error can be very small. If the signal to noise ratio is small, is very small, then we will have like bad link, and then the probability of error will be increasing according to that. So the relation between the probability of error actually is related to the signal to noise ratio, and we have certain version for the signal to noise ratio which is more suitable for the digital communication. Is called the energy per bit per the noise spectral density, and this can be explained in the coming clip. So we will talk about more about noise and the performance measure of digital communication. See you in the coming clip number 4, and thank you very much.